Hi, welcome back. I'm Amy Fuchsteiner, your instructor for elementary algebra. We're going to be working on section 8.6 today, where we're solving some radical expressions, and we're going to finish up with a little bit about the distance formula. There is a lot of practice problems in this one. I go through a lot, maybe more than I need to. So, no harm, no foul. If you feel like you got it, you do a little bit of fast forwarding. And I absolutely would recommend you grab snacks and something to drink. Okay, so we've already done some square root stuff. We're going to be using what's known as the squaring property of equality today with our radical equations. Radical equations are simply equations that contain radicals in them. We're going to be specifically zoning in on square root equations today, and then the squaring property of equality, which basically says if two numbers are equal, you can square both of them and maintain the equality. So no matter what you got on the left side and no matter what you got on the right side, if you square both of them, they have to be equal. If they're equal, and you square both of them, they're still equal. All right? So let's take a look at some of these. I've got all kinds of open markers here from all my different colors. All right, here I have the square root of x is equal to 7. And when I look at that, I have something on the left and something on the right. They are equal. So if I square both of them, I maintain the equality. So the square root of x squared, square root of x, quantity squared, is just going to give me x. And the square root, and 7 squared is going to give me 49. So this tells me that x is equal to 49. And that works. If I were to take the square root of x, I would take the square root of 49, and that would give me 7. Keep in mind we're using principal square roots here, which means the positive ones. Right? If I'm looking at number 2, I have the square root of x is equal to a negative 4. Using the squaring property of equality tells me if I square the left side and I square the right side, that's going to give me x is equal to a negative 4 times a negative 4, which is 16. And this seems like it will work. The square root of x is x. The square root of 16 is a positive 4. It's a principal. We use the principal or positive square roots. We do not use the negative because we know that the square root of a number should not be negative. All right. So while this seems on the surface to work, it doesn't. We have to make sure that we check all of our possible solutions for what is known as extraneous solutions. While it is true that A equal to B, you square both sides, right? The squares are still equal. It is not necessarily true that if you take the square root of both sides, that they are necessarily equal. If A squared is equal to B squared, does A squared always equal B? Not all combinations. Here's something to think about. Let's say you have 9 equal to 9. This is fine. If I take the square root of both sides, technically I have plus or minus 3 equal to plus or minus 3 because each square root is either positive or negative, right? So on first blush, this seems to be true. But what we're saying is that all combinations, positive 3 is equal to positive 3. That one checks. But I could use a negative 3 equal to a positive 3. This does not check. Or I could do a positive 3 equal and use the negative 3 on this one. This does not check. But it does check that negative 3 is equal to a negative 3. So we have to be really careful when we check a square root. And when we check a square root in this situation, we want to make sure that we're using the positive or principal number. Okay? In addition, there is one other scenario where sometimes things just don't work out. And that is that sometimes you get a solution And when you put it back in, you get a negative underneath the square root. And we all know you can't take the square root of a negative number. Because you cannot take the square root of a negative number, you may have a solution that, while it works in theory, does not actually work in practice. So it is going to be incredibly important for us to always check answers when we're doing this particular homework set. Okay? It's part of the reason why I have so many examples. Right, put me on pause. Grab a drink. Water, soda, what else? Okay. All right. So we're going to do some practice solving equations that contain these radicals or square roots specifically. There are 4 basic steps that we're going to be using. We're going to look at the equation and we're going to isolate that square root on one side of the equation. Because when I square it, I don't want any complications. I just want the square root on one side. So as much as possible, I'm going to get that square root and isolate it. Once I have it isolated, I'm going to go ahead and square both sides of my equation. That means I'm using the square root property to square both sides of that equation. I'm going to solve the resulting equations. And lastly, I'm absolutely going to check my solutions. Okay? Let's take a look at the very first one. Going through the 4 steps. I have a left side and a right side to this equation. On the left side, I have the square root of x plus 3. Is that square root and everything underneath it the only thing on that side of the equation? So on this left-hand side, do I only have the radical and everything underneath it? Now, sometimes that's the hard part because everything underneath it can look confusing. But as you look at this is the square root of x plus 3. And I would have put my tail right there, right? To include everything. So everything that's on that side is underneath the square root. So I have isolated that square root. So now I'm going to square both sides. X plus 3 squared. Square root of x plus 3 squared. The square root and the square cancel, leaving me with just x plus 3. Equal to a negative 2 times a negative 2 is 4. So this will give me x is equal to 1. Right? I'm going to subtract 3 from both sides when I go to solve it. Minus 3, and I get x is equal to 1. And then I'm going to go ahead and do the fourth, which is to check. So to check this solution, I would do the square root of 1 plus 3, which is the square root of 4, which is 2. I was supposed to get a negative 2, but I'm not going to because I'm going to use the principal. So this is a no solution problem. Right off the bat, I have an extraneous solution. That 2 cannot work because no square root should ever give me a negative number. If you want, I really should have known right here because I only want the positive, and that's not a positive, right? Don't always be fooled, though. Don't think you know it because we're always going to come up with an example that doesn't work. Problem number 4. On the left-hand side, I have a square root, but it is not the only thing on that left side. If I just look at what's underneath the square root, this is negative 3 times the square root of k. I need to isolate that square root of k, so I'm going to divide by a negative 3. I want to isolate that square root. This will give me the square root of k is equal to negative 15 divided by negative 3 is 5. Now, the square root of k is isolated, so I can square it. I can also square the right side, and I will get k is equal to 5 times 5, which is 25. Now, before I say k is 5, I want to check. And if I check this, I'll have negative 3 times the square root of 25, which is a negative 3 times 5, which is indeed a negative 15. I was meant to get a negative 15, so this checks, and I absolutely have a solution. See, that one was a negative, and it turned out no solution. This one was a negative, and it turned out that it did work. So we're going to have to be careful. All right, here we go. Problem number 5, same idea, left side, right side. The square root of 2x minus 1, that's all underneath the square root, plus 4. The plus 4 is not underneath the square root, so I must move it by subtracting 4 from both sides. So now I have the square root of 2x minus 1 is equal to a negative 7. Some of you see right here. I'm going to square both sides. And I have 2x minus 1 would be equal to 49. I'm going to add 1. So 2x would be equal to 50. And to solve for x, I'm going to divide both sides by 2. X is 25. Before I call it done, I'm going to go ahead and check that answer. That's going to give me the square root of 2 times 25 minus 1 plus 4. So this is going to be the square root of 49 plus 4, or 7 plus 4, which is 11. I was supposed to get a negative 3. It did not work, so this is a no solution. Man, that one was a negative and it didn't work. This one was a negative and it did work. All right, let's keep going. Do you see how it can be a bit like, it's not as straightforward as it seems. Let's try this one. Here I have a 6 minus 2 square root of x plus 1. That square root of x plus 1 needs to be isolated. I'm trying to get this alone. So I'm going to subtract 6 from both sides. That's going to give me a negative 2. Square root of x plus 1 is equal to 4 minus 6, which is a negative 2. Square root of x plus 1, this is the part I'm trying to isolate. I want to get that square root all by itself. It's being multiplied by a negative 2, so I'm going to divide by a negative 2 on both sides. This gets me the square root of x plus 1 is equal to a 1. Now that that square root is isolated, I can square both sides. X plus 1 is 1. Subtract 1 to get my x, and I get x is 0. That's a lot of work to get x is 0. All right, I'm not even sure I'm done yet. We want to check it. So I'm going to check this. I'm going to get 6 minus 2 times the square root of x plus 1, or 0 plus 1. 6 minus 2, square root of 1. Square root of 1 is 1. So this is 6 minus 2, which is 4. And that does check with the 4 I was supposed to get. So this will work, and it is a solution. Oof. Okay, let's keep her going. I've got some more here. All right. These are going to be binomials. Oh, okay. Let's see how this guy works. I think I just broke something. All right. Same idea. Square root on one side by itself. Yes, indeed it is. And because it is, I can square both sides. So this is going to be the square root of r plus 6 squared. So that's just going to be r plus 6 equals. And on this side, I'm going to have r minus 4 squared. So r plus 6 is going to equal. Do not get caught here. This is r minus 4 squared, which is r minus 4 times r minus 4. This is one of our patterns from multiplying binomials way back in chapter 5. We don't want to go too simple here. This is going to be like a first, outside, inside, last kind of thing. Sorry, my pens keep rolling. So this is going to be square, multiply double, square. Right? Square, multiply double, square. So r plus 6 is equal to r squared minus 8r plus 16. I'm going to move the r over and the 6 over. So I'm going to have 0 is r squared minus 9r plus 10. This r squared minus 9r plus 10 will factor. What two numbers multiply to give you a positive 10, but add to give you a negative 9? 10 is, or won't it factor? 10 is 5 and 2, or 10 and 1. This is not going to factor. All of this minus 20 minus 6. Nah, this is no solution. I don't think I meant for that, but it does not factor. So this guy is a no solution. It ain't going to work. R minus 4, 8, 4, 4, 16. Sometimes it happens. 10 and 1. That's going to give me negative, should be a negative 10 and a negative 1, which would be a negative 11 there. And I have negative 9. There's no way I can get a negative 9 by factoring. This guy's a no solution. Okay, let's try the next one. Oh, Lord. Okay, on the next one. I don't think I intended that, by the by, but hey, it happens. All right, notice I'm making these longer because clearly they need to be longer. Square root all alone on one side by itself. It is. I mean, it's a long, messy looking square root, but it's all there. This side, so I'm going to want to square both sides. So this is going to give me an x squared minus 7x plus 15 is equal to an x minus 3 squared, so times another x minus 3. X squared minus 7x plus 15 is going to equal a square multiply double square. Okay, now I can take x squared from both sides. You see the pens roll down to me? I don't know why. They never used to do that. Minus 6x plus 9. Okay, now I need to get all my x's on one side. So I'm going to add 7x. I could add 6x, but that's still going to leave it negative because there's not enough to cover that negative 7. So instead, I'm going to add 7x to both sides. 15 is x plus 9. And then I'm going to subtract 9. So I get x is equal to 6. Beauty. Now, I need to check this. So if I'm going to check this one, I'm going to check the square root of 6 squared minus 7 times 6 plus 15. And I want to see if that equals 6 minus 3. So I want to check always in the original equation. So this is going to be the square root of 36 minus 42 plus 15. And is that equal to 3? So the square root of 36 minus 42 plus 15. So we're going to do 36 minus 42 plus 15. We're going to see what's underneath that square root first. And we're going to get the square root of 9 is equal to 3, which does indeed check. So this is a solution. I'm glad I did all that work and actually have a solution. Beautiful. Okay. Trying number 9. Number 9, we have the square root of w minus 2 minus w plus 4. I'm going to do the left side, right side again. I want to look for my square root. This is going to be the square root of w minus 2. All of that is underneath the square root. That's what I'm trying to isolate. So I'm going to add w to both sides. W, and then I'm going to subtract the 4. So I'm going to have the square root of W minus 2 is equal to W plus 4. I clearly needed more room here. And then we're going to square both sides. So we have W minus 2 is equal to, well, this is going to be a square, multiply double, so plus 8W, and then square the last one. Square, multiply double, square. Now I want to see if this will work. Maybe it will, maybe it won't. So I'm going to minus a W, and I'm going to add the 2 because I want to zero this side out. So I'm going to minus a W, and I'm going to add a 2. You can do that in 2 steps. So we have 0 is W squared minus 7W plus 6. Okay. Are there factors? I've got a quadratic. Are there factors of 6 that will add to be 7? 6 and 1. I need a negative. So this will be 0 is equal to W minus 1, W minus 6. Using my 0 factor property, W minus 1 is 0, or W minus 6 is 0. W is equal to 1, or W is equal to 6. I have 2 viable answers. Let's check them. If I put in a positive 1, I'm going to check 1 up here. If I check 1, then I have the square root of 1 minus 2 minus 1 plus 4 is equal to 0. The square root of 1 minus 2 is the square root of negative 1 minus 1 plus 4 is equal to 0. And the crazy part about this is I cannot take the square root of negative 1. Do you see how we got that piece right there? Cannot take the square root of negative 1, meaning that's an extraneous solution. It looks like it'll work on paper, but it really does not. What if we check 6? If I go into check 6, I have the square root of 6 minus 2 minus 6 plus 4 is equal to 0. 6 minus 2 is 4, so this will be the square root of 4 minus 6 plus 4. Or 2 minus 6 plus 4 is equal to 0. That's negative 4 plus 4, that's 0, and W equal to 6 works. Yikes. Okay, W equals 6. That works. That's good. That was kind of a tough example. Stop. Rewind. Watch that one again. Okay. Problem number 10 is 5c plus 1 minus 1 is equal to c. All right. Let's see how close this one is. Square root 5c plus 1. I want to isolate that square root, so I'm going to add 1 to both sides. And I have the square root of 5c plus 1. All of that underneath the square root is equal to c plus 1. Now I can square both sides. 5c plus 1 is equal to c plus 1 squared. This is going to be a perfect square trinomial, so it's going to be a c squared plus multiply together and double it, 2c, plus squaring the last one. 1 times 1 is 1. Now, I want to solve this, so I want to move the 5c over. Can only work with the 2c, and I want to move the 1 over. That's going to leave a 0 on this side of my equation. C squared minus 3c. Negative 1 plus 1 is 0. Nothing more I can do there. That's going to be a plus 0. So now what do I do? Well, now when you look at this, you have c squared minus 3c. Can't you pull a c out? I have c times c minus 3. These are two things being multiplied together to give me a 0. So either c is equal to 0 or c minus 3 is equal to 0. Meaning c could be 0 or c could be a positive 3. Now we want to check both of them because it could be they don't both work. Let's check the 0. That's going to be 5 times 0 plus 1 minus 1 is equal to 0. So I have the square root of 1 minus 1 equals 0, or 1 minus 1 is equal to 0. So the 0 for sure works. That one worked just fine. What if I check a 3? Then I have the square root of 5 times 3 plus 1 minus 1 equals a 3. So this gives me the square root of 16 minus 1 equal to 3. Square root of 16 is 4. 4 minus 1 is equal to 3. That works. So here is a case where I had two solutions, and they both worked. Neither one of them were extraneous. Right? Okay. I think I did all kinds of examples there. And I don't even know if I did them all. I did not, because here we have examples with two square roots. We got a square root on the left side and a square root on the right side. And they look horribly intimidating. But they're not. Because when you have square roots on both sides, there's just the square root on the left side and just the square root on the right side. Neither of them have anything else, so I can just square both sides. And if the square roots are equal, then what's underneath the square roots have to be equal. So 3g minus 9 has to equal g plus 1. And this equation is by far easier to solve than any of the ones we've had so far. I'm going to subtract the g from both sides. 2g minus 9 is equal to 1. I'm going to add the 9, right? We're just solving. So I have 2g's is equal to 10. Divide both sides by 2. G is equal to 5. Okay. Now I actually do want to check this because we always want to check. The square roots can mess things up. So we're going to check g equal to 5. I'm going to do check 5 there. That's going to give us the square root of 3 times 5 minus 9. Is that equal to the square root of 5 plus 1? So this would be the square root of 15 minus 9 is equal to the square root of 6, or the square root of 6 is equal to the square root of 6. So even though I got a weird square root, it still works. It still checks. And I have a working solution of g is equal to 5. Let's try the other one. Here I have two square roots again. They're both on their own side. There is nothing else there. So I can indeed square both sides. So 1 minus 2x will be equal to x plus 10. I'm going to add 2x to both sides, leaving me with 1 is equal to 3x plus 10. Then I'm going to subtract 10 from both sides. 1 minus 10 is a negative 9 is equal to 3x. I'm going to divide both sides by 3. Negative 3 is equal to x. So I think I have the x value, but I need to check. If I'm checking this, I have the square root of 1 minus 2 times a negative 3 And is that equal to a negative 3 plus 10? So this would be the square root of 1 plus 6. Is that equal to the square root of 7? That's the square root of 7 is equal to this. Yep, that checks. And again, I have a second solution. That works absolutely fine. Okay, we did a lot of square root solving here. Hopefully these examples served you well. If you would like to take a break, now is the time to do it. I'm going to keep going. I'll be here in a minute. All right. The last two goals of this particular section deal with the distance formula. The distance formula uses the coordinates of a graph. So it measures the distance, the straight line distance between any 2 points, and that can be found using the formula. Distance is equal to x2 minus x1 squared plus y2 minus y1 squared. This idea comes from a Pythagorean theorem. All righty. So here we have the distance between the 2 points. I'm going to do this. And we can see this as the hypotenuse of a right triangle. Where we know that a squared plus b squared has to be equal to c squared. There's my right angle. The thing is, the distance in A is from 1 to 5, or 5 minus 1, which is 4. Also known as x2 minus x1. The distance for B goes from 2 all the way up to 10, or 10 minus 2, or 10 minus 2. So that's 8. Pythagorean theorem says 4 squared plus 8 squared has to equal c squared, or c would be the square root of each of these squared and then added together. The sum of the squares of the other two sides, the square root of the sum of the squares. Okay? We've worked this up into a formula so that the distance here is equal to the square root of 2, well, x sub 2. So 5 minus 1 plus 2 minus 10 squared. Or the square root of 4 squared plus a negative 8 squared. Does it matter if I do negative 8 or positive 8? Not if I'm squaring it. If I'm squaring it, it's absolute fine, right? Because 8 times 8 is 64, and negative 8 times negative 8 is 64. So this would be the square root of 16 plus 64, which is the square root of 80. Now, 80 can be factored either into the greatest perfect square, if you like that particular method, or you can do the prime factorization. If I do the greatest perfect square, I need to recognize that 80 is 16 times 5. So this would be 4 times the square root of 5, as I can take the square root of 16, and that's 4. Or if you prefer to use your prime factorization, this would be the square root of 2 times 40, which is 2 times 20, which is 2 times 10, which is 2 times 5. That's how I do that in my head. And then I could pull out a 2 and a second 2. 2 times 2 times the square root of 5, which is 4 square roots of 5. Either method will get you to the same distance, 4 square roots of 5. Now, Most of the time we'll give an exact answer for that, but on some occasions you might have to give the decimal approximation. So we want to make sure that when you're doing that, that you can do 4 second square root 5. Make sure to close your parentheses. That on this calculator will tell us that that is approximately, wiggle equal for approximately 8.94 units. All right. Working through that. There we go. 8.94 units. Perfect. Let's see. I think we've got a couple of problems here. We want to determine the distance between a pair of points. We can do this from the graph itself, recognizing that the distance formula is equal to the square root of the second x minus the first x squared plus the second y minus the first y squared. All right, so our distance is equal to the square root. What do we want to do for x's and y's? It really won't matter. I am going to call this guy x1 and this guy y1, and this guy x2 and this guy y2. Order will not matter as long as you stay consistent. So this would be 15 minus a minus 9 squared plus y sub 2 would be 22 minus 12 squared. I'm going to drag it all the way across and leave my tail there at the end. This would be the square root of 24 squared plus, and that'll be a 10 squared. Dragging that all the way across and dropping the tail. Square root 24 squared is, I want to say 576, but I'm just going to double check. Yep. 576 plus 10 squared, I know that's 100. So this would be the square root of 676. I will probably need to simplify that. So the square root of 676. Okay. All right. So I'm going to do what I do, which is 676. I'm going to divide that by 2. Oops. So 676 divided by 2, and I'm going to get 338, still even. So I'm going to divide that by 2 again. I'm doing my factoring here. 169. Hey, 169 is a perfect square. That's 13. I didn't think that worked, but maybe it does. Second square root, let's try 676 as a number. What am I getting? Oh, it was a perfect square. So this is going to be 26 units. So that's going to be 26 units. The distance between those 2 points. All right, let's take a look at number 14. Same problem. I'm going to make this one x1 and this guy y1. And that'll make this guy x2 and this guy y2. Just to show you that it really does not matter. The distance here would be the square root of x2 minus x1 squared plus y2 minus y1 squared. So that's going to be the square root of 10 minus a minus 9. Hey, that's almost the same as before. And then I've got a negative 34 minus a minus 4 squared. Okay, so this is going to be the square root of 19 squared plus, that's going to be a negative 30 squared. So 19 squared is going to end in a 1. I don't know what 1, but 19 squared. It's going to be 361. That's a square root of 361 plus 30 squared is going to be 900. So this is going to be the square root of 1261. Wow, 1261, huh? 1261. It's not even, so nothing will be divisible by 2. I'm going to check 3. 3 did not work. So square root, I can't pull a 3 out. I can't pull out a 4 because none of the evens will work. I can't pull out a 5 because it doesn't enter 5 or 0. 6 won't work because that's even. 7? 1261 divided by 7. Let's try it. Nope. 8 won't work because it's even. 9 won't work because 3 didn't. 10 won't work because it's even. 11, maybe. Nope. See, 12, it's even. 13, 97. Crap. 97 is prime. Nothing goes into 97. So this is it. This is as far as I can, unless they want a decimal, this is as much as I can do to it. The other one worked out nicely, but this one did not. It's the square root of 1,261. I can't pull anything else out of there. And I know that because it's only breaks down into 13 and 97. 13 is prime, and I know 97 is prime. So that's it. That's as far as I can go. All right, let's try 15 and 16. Same idea, only I'm going to do an x1, y1, and an x2, y2 on these guys. So the distance between them will be the square root of a negative 8 minus 4 squared plus a negative 2 minus 6 squared. This is going to be the square root of a negative 12 squared plus a negative 8 squared. That's going to be the square root. 12 squared is 12 times 12, or 144. 8 squared is 8 times 8, negative 8 times negative 8, which is going to be a 64. So this will be the square root of 208. Square root of 208. Let's do that thing. 208. It's even, and if I divide by 2, I get 104. And if that's even, I get 52. And if I divide by 2, I get a 26. And if I divide by 2, I get a 13. So this is going to be the square root of 2 times 2 times 2 times 2 times 13. So I'm going to check it. 2 to the 4th times 13. And I do get 208. So when simplified, I can pull a 2 out for those and a 2 out for those. I get 4 square root of 13. And there's my distance between the 2 points. That is what it is as a simplified square root. If I needed to know the decimal, I would do 4 times second square root 13. I don't know if you can see it underneath there. Or about 14.42. This is your exact answer. This is the approximation, right? Okay, problem number 16, same idea, only we've got some decimals. Yikes. So this would be the square root of x2 minus x1, negative 9.2 minus 1.8 squared, plus y2 minus y1, negative 2.8 minus a minus 5.4 squared. Okay, so this is going to be the square root of negative 11, negative 9.2 plus, minus 1.8. Yep, negative 11 plus negative 2.8. Oh no, that's just a positive 2.8. Why did I make that negative? Minus, negative. So 2.8 minus a negative 5.4. 8.2 squared. Okay. So 11 squared is 121 plus 8.2 squared is 67.24. So this would be the square root of 188.24. Okay. And for the record, we would not simplify this particular square root. This particular square root with a decimal in it, we would not simplify. At least not here. We would just type this in. This would be the square root of 188.24, or about 13.72. The expectation would not be that you know how to simplify this guy right now. We would usually do a decimal approx on that one. Okay. All right. Now, I think from here we've got some radical equations to approximate. Oh, yes. I think I've just got two though, right? Yeah. Okay, so the formula, couple of model problems. The formula S is equal to K square roots of D relates the speed of a car to the distance of a skid when a car suddenly hits the brakes. The coefficient K varies based on the conditions of the road. So if K is 5.34 on wet pavement, what is the distance of a skid if the driver hits the brakes at 55 miles per hour? Oh, so S is the speed. Speed of the car is S. To the distance of the skid, so the distance is D. When a car suddenly hits the brakes, the coefficient K varies. By varies, we mean it's different depending upon different conditions. All right, so we're going to start with S is equal to K square roots of D. And we know K is 5.34. Right? K is 5.34. Speed is 55. So this will be S is equal to 55 equal to 5.34 square roots D. This problem is just like what we were doing. It's actually a couple of steps back to an easier time, right? We want to isolate that square root of D. So I'm going to divide both sides by 5.34. So I'm going to get 55 divided by the 5.34. I don't think I'm going to get a nice number. I think it's going to be a crazy number. Yeah. So we're going to get about 10.3 is about equal to the square root of D. And so what I'm going to need to do is I'm going to need to square both sides. Now that I've got the square root alone. So I could do this as D is equal to a 10.3 squared. So 10.3 squared is going to be 106.09 units, whatever. They didn't say what the units was. They didn't say if the units were feet or yards or miles. I'm going to guess feet, but I'm just going to leave it units of length because I don't know what the length is. Okay. I do want to point out that I rounded that 10.3. That did not work out perfectly. So if I do 55 and I divide that by 5.34, and I get that answer, and rather than rounding and retyping, I just hit x squared on that, my calculator is going to square that entire answer for me. It'll be slightly different than the 106.09, but how different will it be? 106.08. So the difference here was really minimal, and it's okay. I don't think if I'm actually measuring, I'm going to tell the difference between 106.08 and 106.09. So I think we're probably good at this one. Just be careful because sometimes when you round out those squares and then you go back and square them, the differences can be quite large. They can be quite a big difference. Okay. Oh, this is one of my favorite problems. Okay, on July 2nd, 1937, Amelia Earhart, she's one of my heroes, her last flight left Lae, New Guinea, and headed towards Howland Island in the Marshall Islands before landing in Hawaii. She never made it there. In 2008, bones found on the island of Nikamororo were found to match her known measurements. The map below shows the locations of the original destination and the island of Nikamaroro where the bones were found. How far off course was she? Now, these dimensions are given in latitude and longitude, and you would have to know specifically how many miles were in each unit of latitude and longitude. I've just left them in latitude and longitude. We'll get the multiplier when necessary. Whether or not you recognize this, the distances at the equator for latitude and longitude are different than the distances, say, in Wisconsin or at the poles, just because it's a circle. If you look up Mercator map. Okay. All right. So here's Ley New Guinea. This is her last known landing. And she was headed toward Howland Island here. Bones were found here. So if on the map, Howland Island is at -8, 2.7, and Nikamaroro is at a -4.7, 5.4, what we want you to find is the distance. We want you to find the red line. So we're essentially asking you to use the distance formula. Distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Depending upon your positioning, you would use different ones. I'm going to let this be x1, y1, and this be x2, y2. So I'm going to have the square root of a -0.8 minus a -4.7 squared plus a 2.7 y2 minus 5.4 my y1 squared. Okay. Now I'm going to do -0.8 plus 4.7. To get what that number is, it's 3.9. And then I'm just going to hit the squared. And we get the square root of 15.21 plus 2.7 minus 5.4. That's at -2.7. I'm just going to tap squared. And I'm going to get 7.29. I'm going to add the 15.21. So that's the square root of 22.5, which is going to be approximately, so second square root 22.5. And I'm going to get 4.74. 4.74 units. And I would need to know how those units measured that close to the equator. Whether latitude or longitudinally was, I don't know, 100 square feet or 100 feet or 1,000 feet. I don't know. It could even be in, what's the word I'm looking for? Nautical miles. It could even be in nautical miles or knots. So, but I have a 4.74 units, whatever they may be at that point in the equator. I'm going to guess, I think I recall hearing that she was less than 1,000 miles off course. Less than 200 miles off course is kind of what I remember. But that's just my memory, which fails me at times, especially now. All right. That was the last example I had for this particular sitting. If you made it all the way through this, congratulations. I'm really proud of you. I hope you got some good notes out of this one. And if you run into any problems, please don't hesitate to reach out to me or to the Math Center. Julia and everyone there is more than happy to help. We all want to see you do well in this course. All right. Thank you so very much, and we'll see you next time.